I believe we are live. Give me a moment to confirm over here. We are live. Okay. Is OBS going to behave nicely today?
You're a little vertically squished.
Yeah, I watched. I try and look back at previous lectures and find things that I'm like, okay, I did this, or I didn't like that I did that. And one of the things, I don't remember if it was the office hours or the lecture, but I realized that my frame was quite large, which I'm fine, being super visible. But I realized, I think it was the office hours, with the longer host names, I cut off some of the things I was typing in the terminal. I talked through it so you could still, kind of gather what it was that I did. But I would rather what I'm doing, certainly be visible rather than my smiling face. So I smashed myself. I may adjust it again a little bit later down the road. Make sure this is updating on Twitch. It is. Cool. So today's January 23rd, and we are in week 3 of CSE598. This is one of the few modules that we are running for 2 weeks, and we're talking about microarchitecture exploitation. So this is our schedule. We're going to wrap this up in the next 7 days here. This module is due next week, Monday. And that means that format strings, which historically is a relatively easy module, assuming that you still have those GDB skills and kind of reasoning about memory that we've kind of avoided for this module. There's going to be a return to sanity, right? A return to things that you kind of have seen before in 466. Reasoning about memory, we'll be able to debug things, look at things, and hopefully for pretty much the rest of the semester, everything should be much more observable, right? One of the reasons that I put speculative execution here earlier in the course schedule is because I don't like it at the end, because people tend to not do the last module. And I think this is a very cool concept, and it doesn't require anything else, right? And so by putting it at the front here, we can get it out of the way, and then everything else going forward is going to just use this consistent tool set that we've kind of seen before. Okay, memes. This isn't one of yours. I did notice there were less memes this week than last week. I hope you get to post memes, because it's free extra credit, right? It is a non-trivial amount of extra credit. So if you're struggling on the microarchitecture module, maybe that's a good reason to post memes. This one was from 365, but it does impact us here in this module, and inevitably it will impact us in future modules. There are hundreds of CSE 365 students. I believe 100 plus didn't tackle their assignment until the very last day. It will cause problems. That's going to interfere with us. I'm going to try and synchronize with 365 as far as not having due dates on the exact same time frame. No promises. And if I happen to catch when 365 is having a due date, so we expect kind of this onslaught of issues, I will try and let you know. But again, no promises. That's just if I happen to be aware of it. Question?
At the very least, do we know when they're doing reverse engineering?
At the very least, do we know when they're doing reverse engineering? I do not know currently.
Their due dates are fixed so far.
Oh, so like they have all
Yeah.
the time?
Like all their due dates are available.
Oh, okay. So we could theoretically figure that out.
Yeah, we probably could, but like this class has a fixed schedule, right?
Sure.
But in reality here, I have this flex week. I've got 5 days of flex, right? And what that's for is if we do run into some major issue where the class as a whole, right, we just have a big miss as a class, we'll shift this or adjust this. This is what I want to do. This is the pace that I want to move through the material. But if the class as a whole, isn't kind of hitting the mark, we'll adjust, compress, shift things around, maybe drop a topic. Like, I'm willing to do that. It's not what I want to do, but we certainly can. And similarly with 365 or running any class, you may intend on there being a set pace, but at the end of the day, you want to make sure that you're actually teaching, right? It's not necessarily about, did I run through all this whole slide deck, right? And so things do change. And so once I know what is actually occurring, I'll make sure to try and make you guys aware. So yeah, 365 is an issue, and it will continue to be so. People have discovered kind of the pain of microarchitectural exploits, and I'm glad to see that somebody ran into this particular issue, right? Which is I'm trying to print something, and so now my code doesn't work, right? Because it's one of those things that just doesn't make sense until you see it and realize it, right, for yourself. And I think we addressed this at the office hours, but there were some issues with the tutorial challenges where if you weren't familiar with semaphores or kind of some of the C semantics that I was using there, it definitely could prevent you from exploring the concepts that we intend to explore in the module. Hopefully that has gotten out of the way. As I mentioned, GDB and Python, we aren't really using that in this module. However, after microarchitectural exploits, we will return to the comfy zone of GDB, Python, pwn tools for most of the semester, right? Some of the topics in the second half of the course that are planned may not be pwn tools, but we can certainly play around with Python. Branch prediction, getting the branch predictor to do what you want. I didn't anticipate the jump from level 4 to level 5 to be as challenging as some people kind of found it, because assuming your level 4 is well written, the difference between level 4 and level 5 is like 4 lines of C. They just have to be the right 4 lines of C. Because all we have to do is make sure that we're training the branch predictor correctly. And this led to a large number of conversations on the Discord with a lot of different opinions on like, what is the right thing to do to solve this? And so we had a little bit of trouble there, which hopefully I have time to explore later on here. Grids. So we aren't done with speculative execution, but this is where we're at. So most students are somewhere around 50%, a little bit less than 50% it looks like. We do have some people that have completed the entire module. Props to them. And we do have some people that are a little bit behind the curve. Now, I don't know if those are people that just simply haven't dropped the class or kind of what's going on there. As we'll see in 2 slides, there's a couple, and I don't know if I'm just grabbing the wrong data, like I don't have something synced up, but there's a couple numbers that don't necessarily make sense. So if there are people that are taking the class and your grades page doesn't show what you think it should, like reach out to me. So this is where we were last week. So we see that it's not that these were people that had a whole bunch of stuff done, ahead of time. It is people solving over the course of this week, which is good. As far as class average, this time the actual class average is orange instead of purple. Thank you, matplotlib. And we see that the average for the class right now at the halfway point is a little bit more than 50%. Considering that we're halfway through the module, that's perfectly reasonable to me. I think the class is plugging along. One of the things that you will find doing the later challenges here is the code that you wrote for the first, say, 5, particularly the code you have written up to level 5, can be reused to solve these later challenges, right? So like your idea of timing memory access, that is something that will be reused. The idea of flushing the cache, that's something that will be reused. The idea of training a branch predictor, that's something that will be reused. It didn't explicitly state it, but level 5 was a Spectre attack, right? So you've already built up to doing that. So I want to say, well, I think I have a slide on it. But there's several levels that are Spectre attacks, like explicitly, which means a lot of the code that you've written from level 5 will directly copy pasta apply in future levels. As far as solve rate, this is still raw number, not scaled. But you see how this kind of curve informs us about how the class is progressing and are we making steady progress. I like the shape of this curve It is interesting to note that the past couple days are pretty much flat, but I can blame 365 for that because even if you were trying, you would never succeed with how much activity was on the dojo. What was that, yesterday? Yeah.
Yeah, nothing got done yesterday.
Yeah. As I mentioned, some of the challenges are Spectre attacks, and I think it's worth pointing out. The challenges themselves don't explicitly state what they are. And so here's kind of a roadmap as far as what are you actually doing. Level 6 and 10 are not speculative. This is just a flush and reload. Right? So this is just about measuring memory access. Level 7 and 7.1, 7 has a bug, 7.1 does not have that bug. That's why they're there. Like that, they are in fact the same challenge, just with a bug fix. This is a prefetch attack, which I have not talked about in class, and I do not intend on talking about it today. There is a Discord post that links to the relevant pre-recorded material that kind of demonstrates how that works. I think it's relatively clear. If not, let me know. We'll address it at office hours. 8, 9, 11, and 12 are Spectre attacks, so this is going to be like level 5. If I remember right, 8 and 9 are directly in C, and then 11 and 12 are Yan 85. Meltdown, challenges 13 and 14. Now, Meltdown is not explicitly harder than Spectre, right? And so if you're trying to optimize your time usage, I would consider, so last semester I told people, after you tackle 7, take a look at 13, 14, then go back to 8, 9, 11, 12. I would argue that 13 and 14 are easier than 11 and 12, but that's going to depend on how you kind of reason and think about things, right? I've gotten questions about like how much time should I expect to sink into these things, and that's really hard for me to gauge, particularly on this module, because it's how long does it take for you to kind of figure out why something isn't working? And since this is all mapping conceptual understanding to what you observe, it's very hard for me to gauge how well you understand the concepts to reason about what needs to be changed. I saw on the Discord there was a little bit of conversation about Spectre Meltdown code that's online. I didn't mention it. You're free to definitely pull whatever you want, right? I certainly can't stop you. However, if you just grab random snippets of code that are on Google, like that are on GitHub, hey, this is a Meltdown exploit or a Spectre exploit. There's lots of implementations that are wrong, where they don't actually speculate. So it's not a Spectre attack. It would just be a flush and reload attack. And so be careful about relying too much on outside code resources, because they either may not be correct or may be correct but may not work in the specific scenario that we have here in a challenge. So keep that in mind, use at your own risk. Logistical things. So I had office hours last week. I said it was going to be in room 190. I believe I have pinned down BYAC 260 instead. It's still right across the way here. It is streamed. However, if you do want to have like a one-on-one, hey, here's my code, what's wrong, like what am I missing? I did have a bit of that at office hours. After I end the stream, I'll hang out for a little bit longer. We can sit down, look at what you're working on, and talk through it. However, that isn't necessarily something I can do on stream, so that means you're hanging out for the duration. Adam's office hours. Adam is a pretty busy guy. As he mentioned, he was unable to hold office hours this week on Monday. He is rescheduling them for Thursday, and I checked with him. He is planning on doing it 11 a.m. to noon on Thursday. So if you do want to reach out to Adam or sync with him, he will be available then. I'll also have office hours on Friday. As I mentioned with the grades, there's a couple weird numbers. I believe there's some people that have not entered their ASU ID on pwn.college. If you haven't done so, please do so. That is how I know you're in the class. That is how I can calculate how students are doing, generate grade numbers, and ultimately submit your grade. It also gives you access to the course Discord channels, where we do talk about, have announcements with logistical changes and things of that nature, right? Lastly, don't forget to thank people on the dojo. There has been a lot of conversation. I know I write these lengthy blog posts, and people tend to like those, but if somebody else says something that's helpful, you can right-click on the message, hit thanks. That is giving people extra credit. The more generous you are with other people, the more generous other people may be with you, right? I'm not saying we want to abuse it, but definitely don't forget about it because that is another means of extra credit to help everyone pass this course. So, my plans for today. As I mentioned, if you've solved level 5 already, you've done a Spectre attack. So I don't think it's worth me spending more time talking about how Spectre works, because you've seen the base case example. The later challenges are just a Spectre attack, but in a more complex environment. And that may impact how much measuring you need to do. It may impact how you need to trigger it, right? Because it's not going to be a semaphore to trigger activity. There may be a different mechanism, such as ioctl. There may be some conditions that are necessary in order to trigger the behavior that you want. So what I plan on doing is talking about pretty much everything else, except for the prefetch attack, as I mentioned. One of the things I want to address is M-fences, or why not put fences everywhere? We had kind of this confusion or discussion about this, and so I'd like to demonstrate a little bit why that isn't a good idea. I'm then going to take a quick look at the meltdown example that is in the pre-recorded lecture videos, and then I have self-sabotaged a couple of the meltdown, like slightly modified versions of the meltdown exploit, and I want, hopefully, to have you tell me what you would try and do to fix this, all right, based upon the timing data. So hopefully we can discuss kind of the reasoning and logic as far as why we would make these changes. Does anyone have anything they'd like me to poke at, discuss, throw up on the screen prior to me delving into any of this? Got nothing? Okay. I had one more thing, which I think is important, and that is recognizing those that are crushing it. So, let's look at microarchitecture exploits. I'm probably going to butcher the hacker handles, but I'm going to try. So I got, what, mzacco at 15. That's 100% of the module. They nailed it in the first half. This totally could have been a 1-week module, right, guys? Right, that's what that tells me. N132, they're at 12 out of 15. So they're definitely cruising right along. We got Earthman with 8, Zero at 8, SJ Zoo at 8, and Fahad at 7. So we're moving right along. And you should feel good about that, guys. One thing that's worth noting is this only solves after the module was officially launched with the class. And a number of these online hacker people with 5 are people that jumped in once they saw there were new challenges and just solved the remaining ones, which is why you see so many people stuck at 5. It's not necessarily that they did the first 5 and then 6 was just impossible. All right, I got something here on Twitch. Can I talk about Spectre v2 level 12 if I have time? Maybe. Okay, so first, what did I call this? I'm actually somewhat organized today. I have, is that big enough for everyone to see? Go bigger? Bigger. Okay. So what I'm going to do is I'm going to go back into our speculative game, because we've already seen this code. All of this code is code that is already displayed in lecture videos or prior office hours. So it's not any big surprise here. Now, this is the assembly, we said, where they're doing that measuring, right? And one of the arguments or things that people said is, well, let's throw M-fences everywhere, right? An M-fence is a S-fence and an L-fence, so let's just throw a bunch in here. Okay. Let's see if I can build this. that exist. What is it mad at me for? Oh, curses. Is it curses or end curses? I think it's end curses. Okay, I'm going to remove game 2 because that isn't what I built. And then we will do the same thing with the controller. What is that just called? Controller Dojo? And one thing I probably want to do is make this dprintf on, what would that be, 3, and then at the beginning of main, let's open temp log. Oh, right. Is that gonna work? That's the dojo. Yes. Okay. So now, do it down here so that I'm not blocking it with my head. I should be able to run the game. Apparently not. Live demos, my man. Why are we seg faulting? Open's good, pin CPU's good. Stringed along. Where do we call string along? Uh-oh. Uh-oh. Is that the payback for laughing at me forgetting to drop privs? No. Rub that in. M fences everywhere. Live demo, yeah. Okay. We don't call stringed along. Uh-oh. This whole demo could just be why? Set affinity, and then we immediately segfault after that. What did I do? Okay. I'm going to abandon this unless anyone has a suggestion.
Does game take like a auto descriptor or something?
I don't think game controller does. Game doesn't. Right? Game. It's after we pin the CPU. Right? And so it's like somewhere immediately here, it's string to long, which doesn't make any sense to me.
Does it need the controller to be running or no?
Well, I know controller runs secondly, right? So I run controller. Controller is also going to segfault. What the heck have I done? I don't know what I've done, but it's horrific. Okay, so let's do something different then. Let's make sure this works. I do test these things beforehand. Now, this one does require an argument. Okay, so this behaves. I can do something similar here. It's not as straightforward, but we still have in this Meltdown demo assembly code where we are going to do some type of measure, right? This is not the measure assembly code. I may find where that is. This is in C. So this is the C equivalent that hopefully you've written in some form to time of memory access, right? And so if I throw an M fence above, an M fence below, and let's throw an M fence here as well for good measure. If we run this, and this one just requires an argument, that is still working. And the reason that is still working is because it isn't slow enough. So we're going to just throw in a bajillion M fences because I'm a believer. Okay. If you haven't seen this example, what it's supposed to do is perform a meltdown attack, and then this does a statistical kind of aggregate. So we run 100 times, and then based upon the number of times a particular index won, we predict the value. All right. And I said that this wasn't working because I kept seeing E down here. The thing that we're trying to leak is the string secret message. It's hiding right up here at secret page. When we set up the secret, it is the string secret message. And so that's the value that we're trying to leak. And when I was running it, it kept saying E at the end. And I'm like, well, that's the correct answer. This is lame. But now that I have a bajillion M fences in here, we see that I don't get E, ever. Why do you think this is happening?
It's too slow to get like an accurate measurement compared to like non-guesses, basically.
Okay, so the statement was it's too slow to get an accurate measurement. Why is it slow? Because we're waiting for every single access?
Memory access.
But like if we think about it conceptually here, all of these M fences are essentially a no-op, right? Like if I synchronized everything here, then everything's synced. So then if I synchronize everything here, am I really waiting for anything? No, because everything's already synced. But then I synchronize here, but everything's already synced. So this, like, why does this happen? The answer is because mfence is actually a very slow operation. It's not necessarily the delay of waiting for everything to synchronize, but the act of verifying that everything has dispatched. It is a slow operation. And so in this case, because we're doing a kind of sampling, I had to add a bunch of mfences to kind of show this effect. But if we looked at the code from the Spectre example from the game, or not Spectre, but the just raw memory access timings, we would see that adding a couple M fences will dominate the time. Where the amount of time it takes to perform these M fences is way larger than the amount of time for this memory access to occur. And so including just one extra M fence can be so much that this M fence takes too long. so that this takes more time than the memory access, and you won't get values that make any sense. Everything just will be a big number. That's still working. I love Rob. It is live demos, guys. Twitch also says, because it delays the CPU and other stuff is running in the background, changing the cache. No, it is not because the cache is changing underneath you. It is, if I change this so that this dumps out the time, is that a U64 that this returns? Yes. Okay. If I change this so that we now print this out, we see these are all large numbers, right? These are 800, 900,000, right? But when we were timing just raw memory access, a slow memory access was like 300, 400, where a fast memory access was typically under 200. It is literally the amount of time it takes for the mfence operation to occur inside the CPU. Now, one of the other things that was mentioned, which led to an interesting conversation, and I got to learn something, because I am certainly not the expert here. I know quite a bit, but not everything. And I love it when I get to learn something else. People made the comment of, well, okay, it's really because of instruction ordering, and there's this technical difference between mfence and lfence, and so I can use a bunch of lfences. And so you could do this, and this would probably work, because lfence is significantly got the E. So that still works, because lfence is a significantly faster operation. But I said something weird about like instructions aligning and this, that, and the other. And this led to a very detailed conversation where we had to go into the Intel reference manual and fight over the specific verbiage of what is stated here. So I said that an mfence is the equivalent of an sfence and an lfence. And if you read let's see if I find it here. There's a quick summary of mfence, and it says exactly that somewhere here in the documentation, that an mfence is an lfence and an sfence. Right? Now, in our more verbose example here, it says for an mfence, where's my pointer? Okay. It does serialize load and store operations. An lfence serializes load operations, and sfence serializes store operations. So what I said was not wrong. However, the guarantee that you get from an mfence is that the serializing operation guarantees that every load and store instruction that precedes the mfence instruction in program order becomes globally visible, which means that we've actually gotten the value from memory, right? We're not guessing. Before, and this is the important part, before any load or store instruction that follows. All right, so what gets interesting here on a kind of technical level is what are we doing after that mfence? We're doing RDTSC. Is this a load operation? Am I getting something from memory? No. Is it a store operation? Am I putting something into memory? The act of calling RDTSC itself is not, right? It's just going to load values into registers, as we saw in the assembly example or assembly version of this. And so having this mfence right here technically does not guarantee that all loads and stores are done before this first timestamp, because it's not a load or store. The guarantee of the mfence is all loads or stores preceding will occur before any loads or stores after. but instructions that are not loads or stores are still allowed to proceed. Now, this doesn't make any difference in your code. You can use an mfence here, and it's perfectly fine. You'll get valid results, and I think this is the most sane and straightforward approach for obtaining that timing measurement. We make sure all loads and stores are done, we get the timestamp, and then we make sure that this load occurs before we take the second timestamp. But why was there this argument about, like, well, let's just use a whole bunch of L-fences? Well, what happens in the Intel documentation of an L-fence? Well, an L-fence reads very similarly. However, if we take it at the literal detail of the verbiage, it is in fact different. It says it performs a serializing operation on all load from memory instructions that were issued prior to the L-fence instruction. So far, so good. All loads will be done, right, before we get past this. Specifically, the L-fence does not execute until all prior instructions have completed locally, and no later instructions begin to execute until the L-fence completes. So an L-fence would prevent this instruction from occurring, because an L-fence blocks all instructions until this load occurs. And so if there was any confusion on some of the discussion that occurred, that is where kind of this nitty-gritty differences are. But as far as what gets you a measurement that will work, either one. I think it was worth discussing this a bit because we had some back and forth in general. Okay, nothing else from Twitch there. All right. So, I'm going to ask again, how many people have watched the pre-recorded lecture videos? All right, we're doing pretty good. Pretty good. So hopefully you've seen how a meltdown exploit is different than a Spectre exploit. In a Spectre exploit, we have this branch that we're trying to speculatively get into. With meltdown, and that is inside this like target code that we're exploiting. But with meltdown, the entire thing that we're doing is in our C program. So if we ignore this setup mem and setup secret, because that is just me storing some secret value somewhere in virtual memory, what is occurring here? Well, we have an exploit. It's going to, pre-work is just going to flush things. We have a speculative exploit. And then our post-work is doing this statistical kind of analysis, right? And then down here, I'm reviewing the statistical analysis. So what is different with Meltdown? Well, instead of having a branch that is causing this speculation to occur, we are causing the speculation to occur in a linear set of instructions. Because if you'll recall, the assembly instructions are not executed in order, right? And so if there is something that is slow, the CPU will work ahead. And what we have here a couple weird assembly instructions, but these are floating point operations. So very much how the Spectre exploit was slow from batching something out to floating point. Right here we have some slow floating point instructions. And so we execute this stuff above, then we have some slow operation that will segfault. We see that right here, there's a comment, this is a guaranteed segfault. And so if we were executing everything in order, we would always segfault on this instruction. However, because instructions are not executed in order, what can happen is we will speculatively perform this memory access down here before the segfault gets realized by the CPU, because the segfault depends upon this floating point math. And so it's very similar to Spectre, where we're triggering speculative execution, but we are not doing it with a conditional branch. We are doing it with just out of order execution. Now, traditionally Meltdown, when you talk about it, it isn't done in process like this, right? Because it doesn't make a lot of sense to leak something that is in your current process, right? The thing that Meltdown lets you do is it allows you to leak kernel values. And the reason that that works is because kernel memory used to be mapped inside of every single process. It isn't something that you could access directly on your own, but it is something that you could access. And there is a check inside the kernel for something that's called a supervisor bit. And that is what informs the kernel, or the code, the memory access. Is this access occurring in the kernel, or is this access occurring in user land? And this supervisor bit isn't set before the speculative execution occurs. And so you're still performing a race, but what you're racing is this seg fault. Does it occur before or after this memory access? And this memory access for a true Meltdown exploit will be some address in the kernel that you don't have the ability to access directly. And because you're doing this speculatively, it will load the value in the cache, as we've seen with like level 5, and you'll be able to perform a timing attack to leak values from the kernel. Okay. Let's look at a purposely sabotaged program. So this is supposed to output secret message. This is what I get. It's like almost there, right? Maybe if I just run it 50 times, I'll get the value. And maybe I would. But for the challenges, we need to leak the flag. And you don't necessarily know what the flag is, right? So that means there's no way of me just knowing I'm successful, because I don't know if I got a valid flag byte or not. So what's the first thing that we would probably try and do here? Like, what would I be interested in?
Make it stable.
All right, I want to make it stable. But I want to know why is this not occurring. And the only real thing that I have to reason about is timing data. So let's have some timing data. I'm going to forget to pass this an arbitrary argument every time. So remember, this is the count of timing values that pass my threshold. And what I see here is pretty much everything is passing my threshold. What's something I might want to try and do?
Decrease the threshold.
Decrease my threshold. We see here my cache hit threshold's 460. Give me a number. What do you think's a good number? Doesn't matter. 300. Okay, 300 wasn't low enough. Let's go lower. 200. Okay. Now we see a whole bunch of zeros, and we suddenly have one value. This is out of 100 runs. 99 of them happened to hit that, and for whatever reason, 13 was a close runner up here with 57. So one thing we can do is decrease our threshold. What happens if I set my threshold like exceptionally low? What am I going to observe here? All zero. Right? And that makes sense. So one of the first things that we consider tweaking here is our threshold value. Okay. Here's my second one that's messed up. This one definitely doesn't seem to give me anything. I don't win pretty much ever. And I have a threshold now at 260. Right? You want to bring it down to 200? Since that was the number we picked. Hopefully this doesn't suddenly work, because there should be something else wrong with it. And we see that lowering the threshold here didn't fix my issue. What else could be wrong? All right, we want to see the timing value. All right, so this isn't the raw times, but again, we're seeing everything is a high value. But we have a low threshold. What could it be?
You may wrongly set
Okay, it could be our fences. And what we see here, my fences are wrong. That was a good call. So where should my fences be? What do you think how I should set this up?
set M fence before you complete here.
Up here?
And yeah.
Okay.
And set one after M.
And set one right here?
Yeah.
An M fence?
Yes.
Should it be above the end timestamp?
Well, that's interesting. Well, let's do this and see what we get. Let's see if this fixes it. All right, so that didn't fix it, right? Having that M fence, that second M fence right here. Now, somebody else suggested, what if I put the M fence up above this timestamp?
Do we want it to be an L fence?
Do we want it to be an L fence? Why would an L fence be better than an M fence?
Because, so we talked about before, M fences block the next instruction that interacts with memory, whereas L fence blocks any instruction that comes after it.
Okay, that makes sense. That's good logical reasoning. The statement was that the L fence blocks all instructions, or the M fence only blocks loads and stores, as we discussed, and we want to try and make sure that the second timestamp occurs after the load is complete. Okay. Now, I feel like that was a good change, but we didn't get where we needed.
Twitch has a suggestion. That probably is.
Twitch has a suggestion. What does Twitch say? Didn't clear the cache. My bet is I didn't clear the cache. Okay, so let's take a look here. This is my timing. Am I flushing the cache? Post work, inner work. This one, flushing the cache would occur where? Exploit, pre-work. Okay, so I am flushing the cache. I'm doing it right here. I hate the way I name these functions in hindsight, but yeah, that is just is what it is. So I am flushing the cache. Somebody says, is it prefetching? Could you elaborate? What are you thinking about with prefetching? Right, anyone here? Do you have an idea what they mean when they say prefetching?
So the index you're iterating, it's like predictable.
Okay, so the statement was the index that I'm iterating is predictable. So one of the things that I mentioned was in the lecture videos, and I believe in class, is that you have to beware of your for loops working against you. If you are writing a for loop and it is incrementing like 1, 2, 3, 4, 5, 6, the CPU will try and help you out by loading values into the cache ahead of time, right? And that could work against us. Twitch chat does say that I'm not mixing I, is what it could be, and that goes back to how am I doing these memory accesses? Are they linear? Are they in order? And it says your loop to call flush and reload, I need to mix this out. Okay, well, let's take a look, see if I can figure out where that is in this mess of code. Well, I imagine the answer is right here. Well, we're giving it address, exploit, and then within exploit, we have this right here. So we're saying we probably want to mix this up. I actually don't have I'm just going to yank it from another one. Boop. Okay, so is that the one that I want to mix? What's that?
I don't think so. Because
You don't think so?
Yeah.
That is the flag index. So that's not it. So I'm going to here. What do I want to mix?
The J right there.
You want
Second J.
the second J? All right. Let me grab. Someone else is shaking their head. Why?
Because that doesn't matter. Every data is in the you already get all the data. So that doesn't matter.
It's not here either. Is what am I doing right here? The comment says I'm reviewing the stats data, right? And so this isn't where that access is occurring either. Now I said I'm doing 100 observations or 100 measurements, right? And so what I'm doing here up in this loop is 100 times I'm performing a speculative exploit. And I'm doing this exploit on some target address.
How is the target address set?
Oh, let's go back. That address is exploit's address. Maybe it's in this post work. What are you doing? Okay, well this says mix I. Post work, inner work, post work, internet. Okay, and what is buff size? Okay, so it's disguised here, but what's happening right here is in post work, we do the speculative exploit here, right? We perform this memory access. Then I need to perform the measurement. In this particular piece of code, the measurement is called post work. And we are iterating from I equals 0 to whatever buff size is, and buff size is 256. So I am performing my memory access, or performing this timing one after the other. And that could cause me grief. Let's see if that fixes this. Still no.
The numbers are lower.
I'm sorry?
The numbers are lower, I guess.
Oh, this should be mix I, not I. That was on me. Okay. We're starting to get somewhere. What else could be wrong? Twitch delay is a large debuff. Yeah, it is. So, I mentioned this, and I don't necessarily know that you would guess it. A cache entry is 64 bytes in size, right? And this is iterating via this cache line size value to identify that location. And it is 64 bytes in size. But this is so close together that it will actually impair what you're doing, because the CPU has some other optimization. And so if instead we make this a page size, which is what all the challenges use, all of a sudden it works. Now the changes that we made before were totally valid changes, right? Because we didn't break anything. And we came to those conclusions by thinking about how this works in a conceptual level. But one of the traps that you can run into, particularly with these meltdown challenges, because you are performing the memory access against yourself, right? Try and make sure that the locations that you're accessing are far apart, because prefetching is not the only thing that the CPU can do to optimize against you. It can just be like, oh, well, you're grabbing this, there's probably the thing ahead, there's probably the thing behind. Let's just, pull stuff in here that you're likely to use. But if you're sufficiently far away, then it's not an issue. Hopefully this was helpful for people kind of reasoning about, hey, I see something not working, how do I think about it, what's going on there. If you do have questions about the content, let me know on the Discord. Everything that I showed today is based upon conversations I've had with other students about things that don't make sense to them or something that they got stuck on. And so I want to make that type of example available to everyone. But let me know in the Discord. Office hours, like what I present and show, is based upon your questions. So ask questions, I'll try and help you out on the Discord, or I'll try and throw it into an office hours demo to discuss the topic. All right, with that, I have ran out of time. Twitch does say that 512 is also fine according to the official POC. Yeah, so 64 technically should be fine, but as we just saw, it is not. There is some number greater than 64 that is the limit, but we just try and avoid it altogether by making it a whole page size that's definitely far enough out. Like I said, with that, I'm out of time, so I'll let you all go. If you do have questions, ask on the Discord. I'll try and help you out.